Alright, let's solve this problem. How many positive integers less than 500 can be written as the sum of two positive perfect cubes? So the key to solve this problem is to first identify all the perfect cubes that are less than 500. If you are preparing for the AMC exams, it is best to know these numbers as you do them computationally, or just know them on the top of your head, because in the exam you won't have a calculator available to you. So all the positive integers that are less than 500, which are perfect cubes, can be written as 1 cubed, 1, 2 cubed, 8, 3 cubed, 27, 4 cubed, 64, 5 cubed, 125, 6 cubed, 216, and 7 cubed, which is 343. So that now that we have listed all the positive perfect cubes less than 500, we can realize what the problem is asking us to find. So the problem essentially asks us to find a solution for the sum n, which is less than 500, such that n is equal to the sum of two positive perfect cubes. So the perfect cubes can be written as a cubed plus b cubed. And we also have to realize that a and b can be different or alike. So when we computationally find all the solutions through a case-by-case basis in this problem, we have to basically remove all the solutions which are not unique. So when we combine these conditions, we essentially get a cubed plus b cubed is less than 500. So this is the condition that we have to solve for in this problem. So now that we have this, we can compute all the sums through a case-by-case basis. So for case 1, we can set a equals 1 and increase b systematically and find all the solutions less than 500. So when b equals 1, we have a cubed plus b cubed, which is 1 and 1 in this computation, and we get 2. So now when b is 2, we have 1 cubed plus 2 cubed, which is 9. When b equals 3, we have 1 cubed plus 1 cubed plus 27, which is 28. When b equals 4, we have 1 plus 64, and that is 65. When b equals 5, we have 1 plus 125, and that is 126. When b equals 6, we have 1 plus 216, and that is 217. When b equals 7, we have 1 plus 343, and that is 344. And now, when we have b equals 8, we get a number that is bigger than 500. So we do not want to include this in our solution set for this case. So now that we have finished this case, we can move on to case 2, where a equals 2. So now that when a equals 2, we can also set b equals 2 and solve in a similar fashion. So now we check all the solutions. 2 cubed plus 2 cubed, and that is 16. Now we increase b. b is now equal to 3. So now 2 cubed plus 3 cubed, and that is 35. So when b equals 4 now, we have 2 cubed plus 4 cubed, and that is 72. So now when b equals 5, we have 2 cubed plus 5 cubed, and that is 133. When b equals 6, we have 2 cubed plus 2 plus 6 cubed, and that is 224. When b equals 7, we have 2 cubed plus 7 cubed, and that is 351. So when b equals 8 now, we get a number that is greater than 500. So we do not want to include that, and that is where our case ends. So now that we have finished case 2, we can move on to case 3, where a is now equal to 3. So when a is equal to 3, we can repeat the process and find all the solutions, all the perfect cube solutions less than 500. And the numbers are 54, 91, 152, 243, and 370. So that is where the case ends for case 3. Now we can move on to case 4 and find in a similar fashion, find the solutions 128, 189, 280, and 407. So that is case 4. And now case 5, where a equals 5, we get the solutions 250, 341, and 468. And that is where case 5 ends. Now in case 6, where a equals 6, there's only one singular solution, and that is 6 cubed plus 6 cubed, which is 432. Now we can check case 7, where a equals 7. So in a equals 7, we get 7 cubed plus 7 cubed, and that is greater than 500. 7 cubed plus 7 cubed is 686, and that exceeds 500. So we stop here. So these are all the cases, starting from case 1 to case 6, in which we have all the solutions for the condition. So now we essentially want to check for non-unique values and collect all the unique values and list them. So when we collect all the unique values, what we do is that we go back and check all our solutions and find solutions which repeat. So for our first solution, for our first case, we have 2, 9, 28, 65, 126, 217, and 344. So these are 1, 2, 3, 4, 5, 6, 7. So these are 7 unique solutions here for case 1. So for case 2, we have 1, 2, 3, 4, 5, 6. So these are another 6 solutions. So for case 3, we have 1, 2, 3, 4, 5. So there are 5 solutions here. So for case 4, we have 1, 2, 3, 4. And for case 5, we have 1, 2, 3. So we have 4 solutions here. 3 solutions there, 4 solutions here. And for case 6, we have just this one singular solution. So when we add up all these solutions, we get 3 plus 4. There's 3, there's 4, plus 1. And all the solutions from case 1, which is 7. All the solutions from case 2, which is 6. And all the solutions from case 3, which is 5. And we get 8 plus 13 plus 5, which gives us 26. So one caveat that I would include in this problem is to not just list all the solutions and sum them up, just like I did. Because you want to be careful, you want to go back and see which numbers are non-unique. So let's say you have 189 here. You could have, not theoretically, let's just say 189 is also included here in this case. So if they match, you want to discard the solution. But that is not the case here. So we don't do that here. So these are all the solutions which gives us a number less than 500 for when they're summed as perfect cubes. So the answer is 26.